It's you! Welcome back! It's Nick Does Maths! With Maths, me! It's here! This is where we are. Welcome! Thank you for choosing Nick Does Maths over your mathematical entertainment this afternoon. We will be taking you through a solution to a differential equation, but unfortunately, like most differential equations that we encounter in the wild as you go differential equation hunting, this does not really have an analytic solution. It's non-linear, it's all kinds of horribleness. We've got a sine y in there. Blah, terrible. So what we're going to do is we are going to get a numerical approximation. So we've got a bunch of conditions here. We've got initial conditions at x is 1. We're going to use that to bootstrap ourselves a numerical approximation for the y value at 1.1. Now, this is a second order differential equation, so what we really want is d2y n plus 1 yeah, that's a good enough one there. The n plus 1th second derivative, we are going to approximate with this little chestnut, not over 2h, over h squared. Now, all this is, right, is we are saying, of course, is if we think of this as 3 points, right, we've got xn plus 1, we've got xn plus 2, got xn, and the equivalentyn's and y dashes. What we're saying is, right, is that is the rate of change of the gradient. So we're going to take that as my first gradient, that as my second gradient, and then we find the rate of change of those two gradients. That is all that is, okay? So we are finding the second derivative here in terms of our approximation, and this is just a one-step Euler approximation for the first derivative here and the first derivative here. Now I'll remind you that our approximation, our first order Euler approximation is dyn d, I suppose I probably should put, that's fine, dx is approximately equal to yn plus 1 minus yn over h. Okay, very, very simply put, right, that gradient there. So we would approximate the gradient at xn in terms of these two values and the gradient at xn plus 1 in terms of these two values. Very, very basic, very coarse, very, very jaggedy sort of basic level approximation. It's okay, it does a job, but it is very moody, okay? Very susceptible to small changes in h and so on and so forth. There are nice ones to do this. The really nice thing about using the second order numerical approximation, I really should put a squiggly in there, is that because it relies on the 2 points either side, it tends to smooth things out a little bit, tends to be a little bit nicer, a little bit more accurate, all right? We don't get huge variations in my estimate, all right? Now, in the same way, right, so let's try and use this. This is what we're going to try and use because we've got a formula for that, and then we are going to try and use this to bootstrap up my solution. How am I going to do that? I'm going to use, if I rearrange this, I can get that yn plus 2 is approximately equal to 2 times yn plus 1 plus h squared d2 yn plus 1 dx squared minus yn. All right, so each new value of y depends on the previous two values of y, which helps smooth things out for me. Nice. Right. So let's see what we can do. Let's set ourselves up some values. Have I got my calculator? We've got the calculator. Let's see what we can do. Probably going to use this space in a second. Right, x. Now you're going to use that space a lot in a second. Should we do that there? Should we do that there? Let's do that over here, in fact. Right, so we know what's going on at 1. We know that that is 1, that is 2, and in fact I can get that, the d2y dx squared. Why? I have this formula. So, So, the second derivative is 1 plus x times sine of y, which is sine of 1. Apparently, right, that is 1.8415. And I'm just going to store that as the exact value. I've rounded that a little bit, but let's go. Now we need to pick a value of h. The original question did suggest taking h as 0.05, because then we're only doing a couple steps to get up to 1.1, so 1.05. Right, now, we do have a small issue here, is my formula here, so that would be my n plus second term. It's going to require this y value, but it's also going to require that y value. And I don't have a y value. I need two more y. I need another y value. So, what is left for me? I could just use my first order Euler approximation. I could do that. All right, I could do that, and what would that give me? If I use my first order Euler approximation, that would give me that yn plus 1 is approximately yn plus h times the previous gradient. So that would give me, so the y value here would be yn plus 2 times 0.05. So it would give me 1.1, and I'm up and running. I think we can do better than that. I think we can do better than that. Like I say, just a simple one-step Euler can be a little bit moody. So instead, how about we go for that two-step Euler? So let's look at the gradient at this point here, and the idea is instead, right, because there's always a couple of ways. I could approximate the gradient here by using the next point, in which case my gradient will be too big. I could approximate the gradient here by looking at the gradient here, which will be too small. A nice one to do is to, how about I look at the gradient between these 2 points? I like that one. I like that one a lot. So that will be yn plus 2 minus yn over 2h, because now the distance is 2h. Now that, my friends, is much, much nicer, because that gives me yn plus 2 is approximately, these should all be approximates, is approximately yn plus 2h times dyn plus 1 dx. All right, it's approximately that. Is that accurate enough for me? Yeah. Now then, why is that cool? Well, because we can end up with a really sweet approximation here. If I know this, this is another really nice little bit of approximation. Call that equation 1, call that equation 2. What happens if I add them? What happens if I add them? If I add these two things, minus yn plus yn, they go bye-byes. So I get 2 times yn plus 2 is equal to 2h. Well, what we end up with is this. We get twice the original yn plus 1. That will get divided by 2, so that's fine. Plus 2h dyn plus 1 dx plus h squared d2yn plus 1 over dx squared. So what we end up with is this really cute little approximate version of it. All right, which is actually getting quite close to a two-term Taylor series. You can have a look-see at that one as well, kind of weird. All right, so it's kind of like the one step, but we are taking into account the second derivative to get an even better fit. So that second derivative is giving me an even better fit. All right, so we're not going to get this very, very coarse. I'm not going to use this incredibly coarse approximation here, because I know dy dx at the previous one. So I'm going to make this approximation even betterer. Even betterer. So the next value of y will be the previous value of y plus h times the previous value of dy dx plus h squared over 2 times the previous value of d2y dx squared, which I saved. And I make this, remember, without that, I got 1.1. With it, I get 1.1023. And let's save that as well. Now, funnily enough, I don't need this. I don't need the dy dx, because my actual approximation I'm going to be using is here. All right? It's going to be there. So let's figure this one out. How do I figure this value out? I've got my formula. So it's 1 plus x, 1.05, times sine of that previous y value. So I make this 1.9369, save that as a. Let's go. And now I can find the y value here at 1.1 using this approximation. So it is twice the previous one, plus h squared times the second derivative minus the previous value of y. And I make that 1.2094. Right. Now, that's my limitation whilst I'm stood here in front of the board. I'd quite like to dig into this a little bit more without you just staring at me on a calculator. So let's hop into the Excel lab and see what happens. Ooh, rough teleport, that one. Okay. So up here we have the calculations that we were doing over in the studio. I've got my different x values, my step size here of 0.05. And we've got all of the different steps of my calculation as per before. Reminder here, this y value, we're using our fancy combination of the one-step Euler and the second derivative Euler to get that first value of y, because every value of y after that depends on the previous two. Okay, that's just because of our Euler second derivative approximation. So reminder, the step is we find the y value, we use the x and the y to find the d2y dx squared term using our formula, and then we can just keep iterating like that. Now, with h is 0.05, the y value that we got for x is 0.01, is 1.0945. Now, interestingly, if you remember, we spoke about what would happen if we used our very naive, just brute force one-way Euler for the y value here. So that would have been 1.1, and we're out by 1.2048. So 1.20484 is our other one. I'm going to call it naive. It's probably the wrong words, but that's what I'm going for. In fact, I want that value there. Doesn't matter. All right. We'll go check that at the end. But what I want to look at here is what happens if I make the step size smaller. So instead of 0.05, what do we go to 0.01? Now, obviously, I'm going to take a few more steps here to get to 1.1. And what do we get? If I have an h of 0.01, what y value do I arrive at? 1.20952. And this is the trick that we need to realize, that obviously 0.05 is quite a big, it is a reasonably big step size, but even then, even if I make it that much smaller, I don't get that much more accuracy. So we have to, when we are doing numerical methods like this, we have to consider, and here we are absolutely in the world of, if you're doing this for a project in the real world, you have to consider the computational cost, right? Look how many more steps I need to calculate here by going to 0.001. Oof, we know I've no, where am I at? 1.065. Oh. So you would think that this gets better and better and better as we do make the steps smaller and smaller and smaller. But as you can see here, even with 0.001, I haven't gained that much accuracy, right? To 3 decimal places, 4 decimal places, these all concur 1.2095. So we have to weigh up the extra accuracy from the smaller step size to the added computational complexity that we got going on, which is kind of cool. All right, I know this is beyond the syllabus, but it's quite fun to go dig into a little bit more what goes on. Now, what's also really interesting is this bad boy here. And at this point, with this step size really, really small, what you'll probably very quickly realize is this would make no difference that I used my fancy method or if I use just the one-step Euler. That one doesn't change that much as well. So you've got all these things coming in together, which is why numerical methods for solving equations is like a really big, interesting branch in mathematics. And I think it's really, really cool. Anyway, let's get back to the studio. And pretty cool, huh? By changing that value of h, we can get all kinds of stuff and get better approximations. Really wicked. This is how a lot of differential equations get solved in the real world. There are some more this is very crude. There are more sophisticated methods of getting there, but by and large, there is a huge branch of math studying about how we can use things like this to get solutions to equations that, quite frankly, are not solvable. Anyway, little adventure there together. Hope you enjoyed it. I certainly did. I'm Nick. This was some maths. Please subscribe, like the video, hit the bell for notifications. In the meantime, I got some more next time for you.